Welcome all to the 7th edition of the Geoscience Remote Sensing Society Young Professionals and International Society of Photogrammetry and Remote Sensing Student Consortium Summer School. Well, this year the events brings webinars, roundtables, and tutorials with hands-on, and is organized by two Santa Catarina State universities, UDESC and UNO Chapecó. This event is supported by two scientific societies, the Geoscience Remote Sensing Society, GRSS, and the ISPRS, that is actually the International Society of Photogrammetry and Remote Sensing, and their student branch, the young professionals from IEEE and the student consortium from ISPRS. We welcome all to watch the welcome words of our rectors from UNO Chapecó, from UDESC, and also the chairs of both GRSS and ISPRS. And also to take part of our quiz in both English and Portuguese languages about some particularities of our state, the Santa Catarina state and the southern Brazil. This event is supported by our state foundations, the FAPESC, and two private companies, the Canoinhas Geoassessoria and Instituto Gilson Volpato de Educação Científica. Canoinhas Geoassessoria will make available, in the end of the event, some datasets for a forthcoming hackathon. This event is promoted by different partners that are institutes and universities of Brazil. And so far, we have delivered some webinars, mostly are available online, two round tables, and four actually, tutorials so far. And today, for this webinar, I will just introduce Tatiana Mora Kuplich. She is currently a researcher at the Brazilian Institute for Space Research, INPE, and also a collaborator in the graduate program of remote sensing from the Federal University of Rio Grande do Sul. Her background is actually biology, if I am not wrong.
Yes.
Also from the Federal University of Rio Grande do Sul, a Master Science in Remote Sensing from INPE, and a PhD from England, right?
Yes, Southampton University.
Southampton University, correctly. So she has been publishing the first papers about successional forest stages and forests using different SAR systems. And she will be then taking actually the moderation of these sessions. Tatiana, please feel free. The room is now yours. Thank you a lot actually for accepting this task.
Well, I feel very honored to be here. I thank you for the invitation for this very, very interesting talk. And I think Veraldo introduced my background. I used to work since the beginning with radar images, and now I have my students who work mostly with ALOS pulsar images and also Sentinel-1 images. And well, I think I can introduce you to the two speakers today. Rafael is going to help me to mediate the talk today. He works at the Visona Spatial Technology. He's an electronic engineer from ITA in São José dos Campos. He also has got a master degree in electrical engineer and computation from ITA too. And he's got a PhD also from ITA, and he's been working with change detection in multitemporal SAR images. He's been working with airborne SAR systems, and I think he's going to make a very good contribution to the talk today. And I thank you, Rafael, for being here to help me with this task. And I think now, I don't know if you want to say a few words, and then we pass to Carlos, our main speaker today.
Okay, thank you very much. I just want to say this. Thank you very much for the invitation. It's very nice to be here to see and to contribute with this very nice presentation. Thank you very much.
Okay, Rafael, thank you. Speak to you later.
Yeah.
And now maybe let's call our main speaker, who is Carlos López-Martínez, and we are very, very honored to have him here. Thanks, Carlos.
Thank you.
Carlos is now, he's an electrical engineer too, and he's associate professor at the Universitat Politècnica de Catalunya. And, he worked already in Spain, France, Germany, and Luxembourg. And he's always been working on the microwave remote sensing. And also, I think he's got this, he thinks about environmental monitoring, and his main purpose is to mitigate climate change effects. Right, Carlos?
Yeah, now...
He's being a distinguished lecturer at the IEEE Geoscience and Remote Sensing, and this is very important because that makes possible a meeting like we are having now. He's been supporting the chapter activities and like the summer schools, which are very, very important to bring young students to these matters. And that's it. Today he's going to talk about polarimetry, which is your main interest, isn't it, Carlos?
Oh, great. Thank you, Tatiana. Thank you, Rafael. I'm really glad to be here, and I want especially to thank Beraldo, Rafael, Tatiana for the nice invitation to participate in this summer school. So thanks for the introduction, and without further delay, I'm going to go with the presentation. Let me share my screen.
Okay, have a nice talk.
Thank you. Now, do you see my presentation?
Yes, it's fine.
Okay.
It's there.
Perfect. So, again, thanks for the introduction. So, I'm going to give this presentation that I entitled SAR Polarimetry and Multitemporal SAR Statistical Description. I thought that I would give a quite classical presentation, but I also think that it was nice to present some latest development on polarimetry, SAR, multitemporal, and that's why I put this subtitle on some works we are doing with machine learning, especially focused on classification. So you will see how all these techniques, SAR, polarimetry, multitemporal, can be applied in the new trend of machine learning or artificial intelligence. Okay. Here you have my affiliation, my information, and also my email, where you can send me an email in case you have doubts or you have questions, etc. So, which are the objectives of this lecture? And basically, I divide the objectives into 3 parts. First of all, I will give an overview on the principles of synthetic aperture radar for Earth observation, because sometimes some people don't know which is the objective of this technology. Then, how to obtain physical information based on SAR data, especially when focused on polarimetry, what type of physical information we can derive from polarimetry, and also with multitemporal data. And finally, I will present a particular application on the use of multitemporal polarimetric synthetic aperture radar in the context of machine learning. And in this case, I will focus on the system Sentinel-1 because it's the system that nowadays is the most used one because data are free. You can access the data for free. So this is going to be the outline of the presentation. As I said, first of all, a presentation about synthetic aperture radar. What do we want from synthetic aperture radar? Then I will switch to polarimetry, to multitemporal, and finally I will mix these three concepts in machine learning applications, especially for classification and what type of information we can derive from polarimetry, from multitemporal, from SAR in this context. Okay, so normally when we consider a synthetic aperture radar, we consider a radar that normally is on board a satellite, but it can be on board a plane, a UAV, a car, I mean, any type of moving platform. But normally, when we consider SAR, we consider one-dimensional images. So we obtain one image of a particular area of the Earth surface. But nevertheless, the most important information that SAR can give comes from the fact of having multidimensional SAR data. There are different types of multidimensional type data. Maybe the most famous one is interferometry, where you can obtain information about topography. So in that case, you have two SAR images, and from the phase difference, you derive the topographic information. But in this particular lecture, I will focus on, first of all, polarimetry. So in this case, we will have 3 or 4 images of the same areas. Basically, this polarimetric diversity will make the data to be sensitive to the geometric properties of the targets, and we will differentiate targets according to its geometry. And finally, we will focus on multitemporal SAR. In that case, we can have from 2 to n, ideally infinite number of images, and therefore, in that particular case, the most important applications are change detection due to the temporal diversity, but also to analyze the dynamics of targets, the dynamics of the Earth surface. So let's go first of all to introduce what is a synthetic aperture radar for all of you who doesn't know what is a synthetic aperture radar. So basically, a radar, it's the acronym of radio detection and radar. So basically, this is the most simple scheme of a radar. So basically, in blue, what you have is a transmitter. So it's a system that generates an electromagnetic wave. So we put this wave through a circulator and then to the antenna. Then we produce a pulse. A pulse hits the target. In this case, it's a plane. The target changes the properties of the pulse. And then we receive this changed pulse into the same antenna, and we direct this radiation to the receiver. So basically, the information we retrieve from the target will be retrieved from the changes the target has induced into the signal. So the first property of the signal is the delay, which can be related with the location of the target, with the distance of the target. But beyond that, to detect the position or the range of the target, there are much more changes the target induces into the signal, so we can obtain much more information. For instance, in the case of polarimetry, we will show that the target changes the polarization state of the incident wave, and from this change of the polarization, we will retrieve some geometric properties. Okay? In the case of multitemporal, we will be sensitive to the dynamics. The most important property of a radar, if compared with an classical optical system, is that the system is active. So it provides its own source of illumination. So therefore, the radar system can take images during the day and during the night. It doesn't depend on the solar radiation. So the basic idea is the following. We have a SAR sensor on board a moving platform. In this case, is a satellite. So this satellite illuminates a certain area of the Earth's surface. And basically, what it happens is that the SAR, the system, moves along a trajectory. What we make is that thanks to this movement in the moving direction, we can synthesize high spatial resolution images. The most important properties of the SAR data is, first of all, is a side-looking geometry. Okay, we don't look into the nadir like an optical system. We look into one side. This is just to avoid some ambiguities. Okay, but it induces some small distortions that need to be corrected. SAR images provide two-dimensional SAR images, and these dimensions are the range, which has the dimension linking the satellite with the surface, and the azimuth, which is parallel to the moving trajectory. There are different imaging modes that basically have a compromise between the coverage and the resolution. There are some modes that privilege coverage, so therefore the spatial resolution is coarse, and there are other configurations that privilege the spatial resolution, so they compromise the coverage. Nowadays, there are much more modes that basically try to combine both things. They want to obtain large coverage with large spatial resolution. And finally, perhaps the most striking property of the SAR images is that the pixels, every pixel of the SAR image is complex. It's complex because it presents an amplitude and a phase. So, how images are obtained into the range dimension? The range dimension is, as I said before, the dimension that links the radar with the surface. So, in that particular case, the system sends pulses, like a classical radar. In that particular case, the resolution, which is the capability to detect close targets, depends on the bandwidth. So, therefore, the larger the bandwidth, the smaller the spatial resolution. So, systems with large bandwidth can detect or have a very high spatial resolution. Systems with a small bandwidth have a very poor range resolution. But this is like a classical radar. What happens in the azimuth, which is the difference of SAR with respect to the classical radar? So, if we have a classical radar, our resolution in azimuth depends on the physical dimension of the antenna. So, if we don't make use of the concept of synthesis, this system would have a spatial resolution in the order of kilometers, which basically depends, as I say here, as a conventional radar, depends essentially on the digression, on the radiation diagram of the antenna. A spatial resolution of kilometers is not useful for Earth observation applications. So, which is the difference of a SAR with a classical radar? The basic idea, without going into the details, is that as the system is moving, we can have samples at different positions. So with these samples, we are able to synthesize a much longer antenna. Okay, so in that case, the dimensions or the resolution in the azimuth depends on this synthesized antenna, and therefore, as the antenna is larger, the resolution is higher. In a first-order approximation, as I indicate in this blue square, the azimuth resolution is in the order, more or less, of the dimension of the physical antenna. Normal physical antennas in satellites are in the range of 10 meters, so you have resolution is in the order of meters. And this resolution is now very useful for Earth observation applications. That's why synthetic aperture radars are called imaging radars or high spatial resolution imaging radars, because they are able to provide images with a very high spatial resolution. There is another property of the systems, which is the operating frequency. I mean, if you have already worked with systems, you know that the systems can operate between P band to X band. So which is the characteristics we have with the frequency? Basically, what it is interesting is not the frequency in itself, but the wavelength. The wavelength is more or less the inverse of the frequency. So the higher the frequency, the smaller the wavelength. So therefore, the targets we are able to detect depend on the frequency. So therefore, in X band, where the wavelength is about 3 centimeters, we will be able to see targets of this dimension, 3 centimeters. At L band, we are about 3 meters, so we see different targets. So here you see real images from the Amazonian forest, precisely in Brazil, okay? And you see how they look differently because they are observed at different frequencies. With lower frequencies, we have more penetration capabilities. With X band, we don't have penetration capabilities. So therefore, at X band, we see especially the canopy of the trees. And with L band, we are able to penetrate those canopies and we are sensitive to the ground surface. On the bottom of the images, what you see here is a rain cell, a heavy rain cell. So therefore, at X band, this rain cell blinds the image because the raindrops, are more or less in the dimensions of the wavelengths. So therefore, we are able to see the drops. Therefore, we don't penetrate the rain cell. We don't see the forest. Nevertheless, at L band, this same rain cell is completely transparent. Also, this adds a second property for the SAR image, is that data is almost independent of the weather effects. For instance, and this is one of the most important advantages of SAR images with respect to the optic images, is that SAR images are not affected by clouds. Clouds are transparent. Here, I want to show some examples of the SAR images. This is an open mine in Chuquicamata in Chile. It's the largest open mine in the world. So this is the image, how it is seen by an optical system. And this system, this area is observed almost at midnight. It's at 23 universal time coordinate. So this is how we see the image with the German TerraSAR X system operating at X frequency, about 10 gigahertz. So as you can see, if we compare the optical with the radar, you see that we can observe the same type of details. The only issue is that there are some distortions. For instance, if you see the hole, the big hole, which is an inverted mountain, due to the side-looking geometry, you observe these small distortions that you need to take into account. You have also other examples. You can go from small areas with a very high spatial resolution, you can go to continental applications. This is the case of a mosaicing application in the case of South America, created through ALOS pulsar images at L band. In this particular case, images present a 500 meters spatial resolution. So as you can see from these composite images, you can see that the area of the Amazonian forest presents the largest backscattering. It is white. You also see the Andes mountains, you see the Argentinian Pampa, and you are able to see all the details. So with SAR images, you can go from very local applications to global applications. Okay, so we have seen SAR. So the main property of SAR is to obtain high spatial resolution images of the Earth's surface. But we are interested in more properties about the target. And one way to obtain properties of the target is through polarimetry. So what is polarimetry? Polarimetry is nothing more than the vectorial nature of the electromagnetic field. So in here, we show a electromagnetic field as transmitted by a SAR system. So we send a signal with a given polarization. So basically, as you can observe, the field is indicated by the red arrows. If we cut the electromagnetic field in a transversal plane to the propagation direction, we can see that the tip of the electromagnetic field describes a given ellipse. This ellipse is what is called the polarization ellipse, which characterizes the vectorial nature of the electromagnetic field. So therefore, polarimetry, as I said before, is nothing more than the polarization state of the wave, or the vectorial nature of the wave. There are different canonical states, okay? Different ways in which the field can vary. Perhaps the most usual polarizations for a system, and if you have already worked with polarimetric SAR system, you will see that the system can transmit and receive linear polarization states. In this particular case, you can have horizontal polarization state in which the field only varies into the horizontal direction, as indicated in blue, or you have vertical polarization states. So you have the field varying into the green shape here. It's a cosine in the vertical axis. So these are the most important ones. Most of the existing polarimetric SAR systems transmit at horizontal and vertical polarization states. Basically, because from an engineering point of view, it's very easy to create this polarization state into a wave. But we have other polarization states. We can have a circular polarization state in which the field describes an helix in time. So if we cut the transversal plane, the tip of the electromagnetic field describes a circle. The circle can be described in the left sense or in the right-hand sense. So we can talk about left circular, right circular polarization states. So the linear polarization states and the circular polarization states are the extremes of this ellipse. In the more general case, we have an ellipse. Basically, an ellipse described in one sense, in left sense, or an ellipse described in the right sense. So, why we use polarimetry with a SAR system? So the basic idea is that the SAR system will transmit linear polarization states, okay? The target will change when this echo arrives to the target. The target will change the polarization. This changed polarization will be received, so we will retrieve the information from the target from the change in the polarization states. That's the way we will do, okay? So how a system works. So we have the previous radar system, we have a transmitter, a receiver. So in this particular case, we have a single polarization system. So in that case, we transmit in horizontal polarization and we receive in horizontal polarization, okay? But what happens if we place a second receiver, and this time tuned to the vertical polarization state? So in that particular case, if we transmit H, we receive H and B. Okay? And this is, for instance, with a small change, what the Sentinel-1 system has. The Sentinel-1, the European Sentinel-1, transmits in vertical and receives both in horizontal and vertical. And this is a dual pole system. We transmit in one polarization state, we receive in two. But what happens in that particular case? In that particular case, we obtain two SAR images. The one obtained through the transmission in H, reception in H, and the second one from transmitting in H, receiving in B. And as I said before, this is the case of, for instance, of Sentinel-1. But we have what they are called fully polarimetric SAR systems. What happens if we have also the capability of the second system to transmit? Therefore, we have the previous system, we transmit in H, and we receive in H in B, and we have one column of this matrix, and then we can have the opposite. we can transmit in B and receive again in horizontal and vertical. And this is what is called polarimetry itself. Okay? The system measures the scattering matrix, which is this 2 by 2 matrix. And this is the most important radar observable in the case of polarimetry. The only problem of a polarimetric system is that the pull repetition frequency, I mean, the frequency at which we repeat pulses in transmission needs to be doubled to accommodate both polarizations, needs to be doubled, and this reduces the swath, the coverage area by the SAR image by 2. So this is one drawback of the polarimetric SAR systems. Okay? So what do we have with polarization? Sorry to go again. We have this 2 by 2 matrix, and indeed the element 1, 2 and the 2, 1, SHV, SVH are equal in the case of monostatic system where the transmitter and the receiver are placed in the same position. So we have 3 SAR images. Okay, we have 3 channels. HH, we transmit in H, receive in H, we transmit in B, receive in H, we transmit in B, and we receive in B. Okay, and this is the first observable we have with polarimetry. We have more information channels. Okay, so we have more information, but perhaps the most important observable in polarimetry are not the single SAR images, but the correlation, the statistical correlation between the matrix. Okay, the correlation is calculated in this way, in this expression in gray, but basically this expression tells us how similar are these 2 images, this pair of images. So in that particular case, we have the correlation between the first and the third, HHBB, and we have an amplitude and a phase. The amplitude basically tells us that when it's close to 1, because this is a normalized quantity, when it's close to 1, it means that both images are statistically equal, and which they are, when this parameter is equal to 0, it means that the images are statistically different. And out of this parameter, the most important observable is X, because as we will see, from this phase measurement, we will retrieve information about the geometry. If some of you they know or have worked or they know SAR interferometry, you can already identify that in the case of interferometry, okay, which is a completely different type of diversity, this phase contains the information about the topography. In the case of polarimetry, this phase basically contains the geometry of the target, the type of target we are looking at. So therefore, if we make this combination, okay, HH plus BB, okay, whenever this quantity is big compared to the other 2, as we will see, we can already identify that the area is dominated by surface scattering. So we can say that that area is bare. And this combination depends on the addition of these 2 terms, which is controlled by the phase difference between the 2. We can create a second parameter, HH minus BB. When this quantity is very big with respect to the other 2, we can say that we are in front of double bounce scattering. Where do we have this type of scattering? One possibility is the double bounce between the surface and the walls of houses. So therefore, this mechanism will be dominant in urban areas, for instance. Another type of target where this mechanism can be dominant are forests, in those cases in which we are able to penetrate the canopy. And this happens with low frequencies, L-band, P-band. So therefore, we have the double bounce between the soil, between the surface, and the trunks. And finally, we have HV. Whenever this element is big, is large with respect to the other 2, we are in front of volume scattering. And where do we have volume scattering? In the canopy of the forest, for instance, or in agricultural crops. So as you can see, the polarization is sensitive to to the geometry of the target. We are able to distinguish different types of target. We can characterize different types of target. We can differentiate originally between surface scattering, double bounce, arc volume. What happens if we combine these three into an RGB composition? So here I have plotted some images in the south of Madrid, which is the capital of Spain. This is the single SAR image, black and white, because it only depends on the power. But what happens if we make that previous combination? If we give color to the image? So remember, SH plus SBB corresponds to surface area. So therefore, we can see that whenever this image is blue, we can already say that the area is dominated by the surface scattering. What is happening here? When the area is in red, okay, what we have is double bounce scattering. So basically, the urban areas, like these points in here, I mean, they are more or less red, okay? But there is a clear mechanism. As you can see in this image, you have, in the middle part of the image, more or less, you have a red line. And this red line is a power line. So therefore, we are able to see a clear double scattering between the surface and the power line, because the power line is made of metal, and therefore it has a very high reflectivity. So that's why in this particular case, we are able to see the position of the power line. Finally, all the areas in green correspond to volume scatter. So on the left, we are sensitive to the forest of these areas, and on the right, what we can see is the crops that are dominated by the volume scattering. Here is a second image. This corresponds to the city of Santiago de Chile in Chile. So you have the city in here, and therefore you have surrounding the mountains of Santiago de Chile. What happens if we give color to that image? We see the geometry. For instance, remember, blue corresponds to surfaces. If you go to the bottom part to the left, in this part in here, you see a lake, which is totally flat. Also, you see blue on the top of the mountains, because the mountains surrounding Santiago de Chile, they are so high that on the top, they have no vegetation. The tree line vegetation, or the tree lines, correspond at mid-height of the mountain. So therefore, in the bottom part of the mountains, you see this vegetation, you see these green mechanisms. And also, you can see the urban area, and in those areas where the houses are well aligned with the trajectory, you see basically the red, due to the double bounce scattering mechanisms. In here, you have a close-up of that area. So therefore, you can see that in some areas of the city, you have a clear red mechanism that corresponds to double bounce, because in that case, the walls of the houses are well oriented. So you see a perfect D-plane, a perfect double bounce. In the other areas, you see in green, you see volume, because the houses are not well oriented with the satellite. So you see multiple scattering mechanisms, not double bounce, which mimics what happens in the case of a volume scattering mechanism. Okay? So we have SAR, which are able to give high spatial resolution images. We have polarimetry, that are able to give information about the geometry. What happens if on top of that, we put multitemporal? So therefore, we are sensitive to the temporal behavior of the targets. So in that case, what we have is a series of 8 SAR images acquired between April and September in the Netherlands. So it corresponds to agricultural area. So according to the summer period in the Northern Hemisphere, normally the crops grow in summer between April and September. So what do you see? At the beginning of the season, in the image number 1, you see that nothing is planted. Everything is bare. Everything is blue. But as the time passes and the plants grow in that area, what you see is the growing process of the plant. You go from blue, bare surface, to green, that corresponds to the volume that is originated by the plant. In the case of temporal information, there are 2 very important parameters. First of all is the revisit time. I mean, which is the time between acquisitions. And in order to be sensitive to the mechanisms, we need to minimize it, okay? The other important parameter is the length of the temporal series. And we want to maximize the length of the time series in order to be sensitive, for instance, to seasonal effects. This is the case of how do we obtain revisit time. Revisit time nowadays is the most difficult parameter to obtain because with a single satellite, we are able to obtain more or less revisit times in the order of 12 to 24 days, okay? 1-2 SAR images per month. The only way to decrease the revisit time is to use constellations, is to use more than one satellite. So in that case, I show you how the Sentinel-1 takes images. So as you can see, the constellation of the Sentinel systems is 2 satellites, Sentinel-1A, Sentinel-1B. With this combination of 2 satellites operating in counterphase at 180 degrees, you are able to obtain revisit times of 6 days or 6 days between images. And nowadays, this is the state of the art in the case of systems, of orbital systems, okay? In the future, there will be the Roselle, which is the Sentinel-12, if I'm not wrong, which will be a SAR system on at L1 that will operate at 3 days spatial resolution, temporal revisit time, okay? And for instance, the Argentinian colleagues, they launched the SAOCOM system, and satellites, SAOCOM 1A and 1B, and with 2 satellites, they are able to obtain a revisit time of 8 days. That means that you revisit the same area 8 days. The separation between the images are 8 days. Of course, if you want to decrease even more, you need more satellites. And in that particular case, there are already some private initiatives, the company ICE or the company Capella Space in the US, that they plan to launch constellations of small SAR satellites that are able to obtain images every day or below 1 day per image. But these are private companies. Okay, there are other possibilities, and then we have to move from orbital systems to ground-based SAR systems. So this corresponds to a system we have developed here at UPC together with a company, with a private company, which we have developed a GBSAR system, which is able to operate at 5 frequencies. It's able to operate at P1, L1, S1, C1, X1. And we use this to make scientific studies. In this particular case, the system moves along this rail. And in this particular case, we are able to obtain images in the order of minutes. So we can be very sensitive to the image. So here is to show which is the area we have observed with this satellite. We place the satellite in this point and we look at this forest, and we have 2 corner reflectors in this position. This is the area we observe. We are observing this forested area. This is how we see X1 in the temporal series. So we see basically the canopy. That's why you see the movement. You see the movement of the leaves. Okay, and as we decrease the frequency, the image starts to be more stable, because in that case we are no longer sensitive to the vegetation, but the surface underneath the vegetation, so which is more stable. This is the case of Elban. So you see the red areas are very stable. So that means that we are looking below the vegetation. And this is the lowest frequency P-band, and you will see that there is almost no movement because the areas are very stable. Of course, the images look different because associated to the frequency, we have different spatial resolution. Okay, so what we have until now? What we can obtain with synthetic aperture radar? As I have shown, or as we have seen, we can obtain high spatial resolution. With polarimetry, we are sensitive to the geometry. And with the temporal SAR, we are sensitive to the temporal changes. So we can use all this information for very important applications. And maybe one of the most important applications nowadays is classification. We want to classify the terrain. We want to make the land cover. And in this particular case, I will focus on classification strategies for Sentinel-1 data, because Sentinel-1 has both polarimetric capabilities and multitemporal capabilities. Okay? I will show this this strategy in the context of a project we have developed in the context of the European Space Agency. So in this particular case, what we were using is the temporal coherence. I mean, is the correlation that appears between temporal images. So this correlation information is sensitive to the type of target. So here I show you some example of correlations between images in the southern Spain. Is Doñana, which is the largest wetland area in Europe. And on the left, you see the correlation between 6 days and the correlation between 18 days. So what do you see here? With 6 days, you see the correlation is very high, white, and the correlation is very low between 18 days. So, of course, as the longer the temporal, the correlation between temporal images, the lower the information content, except, for instance, in this area here, where you see that the correlation is quite stable. So basically, what you can see is that urban areas, like here or like here, you see that the correlation is very stable. If you look at this area, okay, you see that the correlation is stable because the urban area does not change, okay? Some other areas like crops, in this particular case, rice or corn or water areas, what you see is that the correlation decreases. So, as you can see, we are sensitive to the dynamics of the target. So therefore, we can use this information to classify the targets. We can use this temporal information to classify the targets, together with the polarization, because each target presents a different polarimetric signature. In the context of this project, you can already see the explosion of information. For instance, in Doñana, we were using Sentinel-1 images, 51 acquisitions, okay, during 2 years, 15 and 16. If we combine all these temporal acquisitions in interferograms and we make the correlation, you can see that we obtain more than 1,000 images, more than 1,000 interferograms. We analyzed also Italy. In that particular case, we had almost 40 acquisitions with more than 700 interferograms. And in Poland, we were analyzing the forest. In that particular case, we had 56, and we had more than 1,500 interferograms. So, as you can see, already these numbers show us that we are in front of a big data problem. This is where remote sensing is going nowadays. We are moving from a remote sensing 1.0, where the focus was on the systems, on the physical interpretation, And we are going to a remote sensing 2.0, where the interest of the focus is on obtaining information from large data sets of images. So therefore, we need to use techniques able to explore this information. In this particular case, we were analyzing different classification methodologies, most of them in the context of artificial intelligence, machine learning, because they were the techniques able to provide such amount of information. So we were comparing different methodologies, random forest, eigenvalues, temporal dynamic indices, etc. Even neural networks, okay? All of them were using the temporal information through the temporal baseline, okay? Combining or not all the images, and the polarization. And we consider also the intensity. The question here is an overall analysis. So you have the three datasets, Doñana in Spain, South Tyrol, in Poland. What happens if we use the coherence, the intensity, or the combination? And what happens if we use polarimetry? If we use the polarimetric channel separately, and what if we combine all of this? So the main lesson of this big table here, well, this table in here, is that polarization increases the classification rate. Why? By the simple fact that we are sensitive to the geometry of the target, so we can discriminate even better the targets that with single polarization. Also, if we use the coherence and the intensity corresponds only to the time series of SAR images, okay? And the use of coherence means that apart from using the single SAR images, and in the case of polarimetry, we are also using the correlation between SAR images. So in that particular case, we see that if we are able to use all the temporal information that comes from the intensities and with the coherence, we improve even more the classification, okay? So for instance, in the case of Doñana, we arrived to a more than 80% classification accuracy. In the case of Italy, it's a very difficult classification problem because the area is on the Alps, a very high mountain, so we have a lot of problems. So it drops up to the 74, and in the case of Poland, we go into the 75, which are very good numbers for classification accuracy. But in this particular case, we have we put ourselves some questions. We are showing the classification in terms of the overall classification accuracy. So we have no discrimination of the classification accuracy. So our question is that if the classification accuracy is uniform or not between the classes. That means that if we are able to classify some classes better than others. And this is a quite classical problem, okay? The second approach is that, as you will see, we are using polarimetric. We are using temporal information and many temporal samples. We wanted to discriminate or to investigate if all these features contribute in the same way to all the classes. That means that are we using the same parameters to classify, for instance, water or to classify rice? Or each class uses different features. And also, something which is not still answered today is how the classifications use the temporal diversity, okay? And we try to answer these questions in a kind or in a framework of machine learning. The problem is that nowadays, neural networks, to simplify, are not able to give information about how they use the information. So therefore, we use a context of self-explanatory machine learning. So in that particular case, we were focusing on random forest because random forest is able to give information about how the system is using the information to classify the different classes. So this is the data set we have. As I mentioned before, we have the Doñana, a test site in the southern of Spain. We have a ground truth to train the data. So basically, what do we have? We have almost 50 temporal images. Okay, we have the ground truth, and we can train the classification. And which are the temporal features we use for the classification? We use the intensity values in BBBH for each of the temporal sample. We use the coherence between the images, and in this particular case, we were using only coherences up to 24 days. Coherences above 24 days for larger temporal baselines are useless in terms of coherence, because the coherence are 0. And also we were using polarimetry. So what happens? For every pixel, if we put together all the temporal samples, all the intensities, all the coherences, and all the polarizations, for each pixel we have more than 500 features, input features. So the question we asked ourselves was if the system uses all these features. So this is the classes we have. We have some artificial surfaces, which are urban areas, commercial areas. We have vegetated areas, mainly agricultural areas. We have some classes with forests, and with some classes with water. So we use the random sample. So basically, the random sample is a decision tree. In the terms of random, is that we have many decision trees, okay, random decision trees that take also a random number of features. So therefore, in order to obtain the final classification, what we make is the aggregation of all the results of all the these random forests or the decision trees to make that decision. So basically, the parameters we were using is a system that has 400 of these decision trees, and each one only selecting a maximum of 50 samples, of 50 input features, sorry. Using this scheme, we were using 20% of the samples for training, and then 80% of the sample for test. Okay? So we have the classification accuracy per class. We can analyze. Okay, the accuracy. We can also analyze how each feature contributes to the final accuracy, but also we are able to combine both, and we can obtain how each feature contributes per class. So we are determining how each feature contributes for the final classification of the class, and we want to see if all the classes are classified with the same feature, or the same class or different classes are classified with different features. And this is still today an open question. So for the accuracy per class, this is somehow very easy to obtain, which basically is derived by the confusion matrix. So as you can see, we measure this accuracy per class with the F1 score, which basically tells us how good, how bad we are classifying a class. So here you have the classes, you have the F1 score, and you see that some classes are poorly classified. For instance, the class 200 that corresponds to vegetation obtains a S1 score of 0.7 more or less, and you have other classes that have more than 0.9, where the maximum is 1. So therefore, you see that the classification accuracy per class is not homogeneous. What happens if we analyze into that global classification accuracy how the features contribute to the final classification? So as you can see here, we have put all the 519 features together. So we have the intensities, we have the coherencies, we have the polarization, etc. So this plot basically indicates the importance of a given feature for the final classification accuracy. So as you can observe, we can identify that there is a set of minimum features that contribute the most to the overall classification. So, and you can see also a Q where the contribution of many features is very low. The problem with this plot is that we lack temporal information. We want also to see how time contributes. Here, you see a zoom of this area, and you can see that you have here all the features, and there are a small set of features that contribute the most to the final classification, okay? But as I said before, we don't have temporal patterns. In order to do that, we analyze this following type of curves. So what do we have in here? On the x-axis, we have the temporal samples, okay? On the y-axis, we have the intensities and the coherencies, okay? The circles correspond to the HH polarization, and the hexagons corresponds to the BB. And finally, the size of this circle and this hexagon corresponds to the input, to the importance of the feature, okay? There are, in this particular class, which corresponds to urban areas, you can see that in order to classify this particular class, the most important observables are these intensities in here and these intensities in here, okay? And also these coherences in here. And I want to highlight this part because this part in here corresponds to 6-day coherence, because the Sentinel system started to operate at 6 days at the end of 2016. All of them, the rest are 12 days, and these are 6 days. So therefore, already you can see here that the shorter the coherence, the higher the information we have. Okay? And this is for the first class, continuous urban fabric. What happens if we, what happens if we make the same for the rest of the classes? Here you have urban areas, okay? Urban areas, industrial areas, construction sites. In here you have agriculture, non-agricultural arable land, irrigated land, rice fields, pastures. And you see that the plots are different. So you see that different features are contributed differently to the classification rate of each class. But nevertheless, you can observe that there are 2 time samples that contribute more or less equally to all the classes. We have the other classes, and you can observe the same type of behavior. Apparently, there are some temporal samples that contribute the most to the classification accuracy, okay? In this case, the last 4 classes are a bit different because in this case, we are talking about, or we are analyzing water surface, inland marshes, salines, water bodies, and marine waters. So the behavior is quite different. So our question here, observing these 2 plots, is why the system was classifying or was using specifically those temporal samples. And I can advance you already that we still today we don't have an answer to that question. We don't know why the system was selecting those temporal samples, but we have some very useful information, as I will show. Okay, so combining all the information, we see that the intensities have more important than the coherencies, and the vertical has more important than the vertical horizontal. Okay, the quotient between the intensities BH, PB is irrelevant in this particular case. Okay, and if we consider the temporal baseline in urban area, okay, the most important coherence is BB because the importance of the double bounce scattering. So you can see that BB helps to classify urban areas, and in the case of agricultural areas, the importance of the features are higher in the case of BH because BH is more sensitive of the volume scatter. Okay, so this is with respect to the importance of the features between the different classes. But what happens in time? Okay? Normally, the random forest looks for the best possible features. Okay? It tries to identify the best possible features to discern, to classify the different classes. Okay? And we have seen that some temporal samples have higher importance than others. So the questions, okay, if we look at this temporal sample, is what happens if we select those temporal samples a priori and we reject the rest? Of course, we will decrease the number of input features. So what do we do? What are the combinations we did here? First of all, we have the optimum classification. We use all the temporal samples and we obtain an overall accuracy of almost 90%. Okay? We use all of them. What happens if we use only year per year? If we use 2015, of course we reduce the number of temporal samples, but the classification accuracy does not decrease that much. We go from 90% to 86%. If we choose 2016, of course, we reduce the number of features. But look, here we are almost 80%, 89%. Okay, so having this, we said, okay, let's take only the best 10 temporal samples and the 20 temporal samples we have identified in the previous sample. So look here, we go from 519 samples to only 70. And our classification accuracy does not drop too much. We go from 90% to 80%. If we take 20, we end up with 140 samples, and we are almost 89%. So we have a tremendous reduction in the number of input features, but our classification accuracy does not reduce that much. The other question was why, instead of selecting the optimum 10 or the optimum 20, we select 10 random or 20 random time samples. Okay? In that particular case, I mean, of course, the drop of the classification accuracy is larger because we end up with 82 in the case of 10 random samples, but in the case of 20, we end up with 87. Okay? So what is the reading, or which is the lesson of all these tests? Is that the temporal samples can be reduced by 80%, which is a lot, okay? But the classification accuracy only drops at 3%. So if we make a reduction of the samples, we can reduction in terms of we can reduce the computation power and the needs of the storage. I mean, we can reduce those needs by 80%, and only we suffer a drop on the classification accuracy of 3%. The other reading we can have is that we can use this excess of resources, because we reduce the temporal sample, not in order to reduce our computational power or our computational storage, but we can use this excess of resources to improve even more our classification accuracy. So that means that when considering machine learning approaches, we don't have to look at them as a black boxes, and we don't have to put all the input features in our system. These results already demonstrate if we make an intelligent choice of our features, we can improve a lot our classification accuracy. And this is the main lesson learning of the of the multitemporal data. So, of course, there are many open questions. It's why the system selected those particular dates. This results is only one data set. At the moment, we would like to test these results to other data sets to see if we have this repetition of results. Okay, now we come to the end of this talk. So, which are the take-home messages I would like you to bring home? First of all, SAR systems, respect to the SAR system. So you have to, I hope you have learned that SAR systems allow to obtain high spatial resolution information about the Earth's surface independently of the weather conditions and the day-night cycle, because we are talking about microwave active systems. If we have polarimetric diversity, we are sensitive to the geometric properties of the target, also to the dielectric properties. We are also sensitive to the soil moisture, but in this lecture, we haven't focused on that. And also, with multitemporal SAR data, you are sensitive to the changes. And also, if we use all this wealth of information to applications like classification in the context of artificial intelligence, my recommendation is that you don't apply blindly multitemporal pulsar data to these new techniques, because an intelligent selection of the inputs, an intelligent selection, and adaptation, if you adapt the the networks, the system, to the particularities of SAR data, you can obtain much better results in terms of classification. Okay, and with this, I would like to finish my presentation, and now I'm open to answer your questions. Thank you.
Thank you very much. I think you teach a lot because you have a very didactical approach. It was very nice. We have some questions here, but maybe I'd like to start with something that I was wondering. Carlos, I live inside the Brazilian Pampa. You know, I am at the extreme south of Brazil, Rio Grande do Sul state, and we have the same Pampa as we have in Uruguay and Argentina. And we've been working on trying to classify the different levels of degradation of these grasslands. And you think that Sentinel-1 images have the potential to help us studying grassland vegetation?
How high is the vegetation?
Oh, it's very low. It's like, I don't know, 30, 50 centimeters.
So therefore, it's like agricultural things. I mean, they are very short. So therefore, with C-band, with Sentinel, you have a lot of potential to use Sentinel data. Why I say this? Because with C-band data with such a short vegetation, your electromagnetic radiation will be able to penetrate and to obtain information from both the canopy of the plant and information from the soil. So as you are sensitive to these two scattering mechanisms, of course you will have a lot of sensitivity to derive information for many applications. So there is a lot of potential. For instance, I saw that a couple or 3 weeks ago in Europe, they released the first crop map of all Europe using Sentinel-1.
Oh, that's great.
Yeah, I think it was published in Elsevier, okay, and Elsevier remote sensing. So it was quite nice because they are using both the polarization, BBBH, to discern the different type of crops, which for me, I mean, I'm not an expert in agriculture, but I think your problem is very similar of the problem of classifying crops.
Yes. Yeah. Thank you.
And also, if you use the temporal information, and this is maybe for me the most important advantage of Sentinel-1 is the possibility to exploit the temporal information.
Mm-hmm. Yeah, you've showed that. It's just amazing. Yeah. Maybe Rafael wants to comment something.
Well, thank you very much for the presentation. Congratulations.
Okay, thank you.
Congratulations also. I don't know if it's only here in Brazil, but today is the Electronics Engineering Day. Then congratulations. Congratulations.
Thank you.
as well.
I didn't know it. I didn't know it.
Yes, yes. I work with airborne SAR, and in the airborne SAR, in our system, we have polarizations as well. And one of the most difficult challenge, the biggest challenge we have, one of the biggest challenges is to separate the polarizations mainly because of the movements of the airplane. All polarizations are mixed. We don't have a poor a poor VV. In the truth, they sometimes or every time they are a little mixed.
Okay.
I would like to ask you to talk about this with the people, because I don't know if with SAR or with the orbital SAR, with SAR from satellites, if we have the same problem. And how can I do to separate these polarizations to do everything you showed?
Okay, for polarization, I mean, you have to go to the engineering part of the system. This is the issue. So first of all, in order to have polarization purity, you need antennas with a large polarization rejection rate. I mean, you need the polarization separation to be below or above 25 dBs. I mean, this is a rule of thumb. It's not. There is no equation that brings this 25, but normally when talking in the systems we have developed here at UPC or talking with colleagues from Canada or from Europe, normally you want the antennas to have a polarization separation higher than 25 dBs. Otherwise, you end up with the mixtures. And the second point, especially with fully polarimetric systems, is that the polarization, the quality of the polarization depends on the calibration step. Okay, and this is quite critical. For calibration, either you use point targets, okay, you use corner reflectors, or you use even active reflectors to calibrate the system. And you can use also distributed targets as the Amazonian forest, okay, to make the calibration properties of the system. So normally the orbital systems, they use the Amazonian forest because it's very homogeneous to calibrate the images. Every time they pass over the Amazon, they use some pictures, some images to calibrate, and also they have calibration sites. I mean, distributed all around the world. They have 2 or 3 calibration sites, and each time the satellite passes over this area, they calibrate the system. And normally you can see that because when you look or when you use images from the systems, sometimes in the headers of the files, you have the calibration parameters or the calibration constants that you have. So for me, these are the 2 points you have to emphasize when using polarization. The polarization purity or isolation, polarimetric isolation of the antennas, and also the calibration. And these when developing polarimetric system, these are key to obtain high quality data.
Okay, thank you very much.
Yeah, it's very interesting. I remember once we did some calibration experiences with corner reflectors in Amazonia many years ago. I think it was for the preparation of the Canadian SAR system, the radar SAT. Yeah, and this is, I think it's a very important part. Was there, can you tell us which were the calibration sites for Sentinel, just for curiosity?
I don't know which are the, in this I cannot help you because I don't know which are the calibration sites. For sure, they will use Amazonian forest for distribute target, inhomogeneous classification, but for the particular sites, I'm sorry, I don't know the. Normally, they tend to be deserts because they put the targets and they don't have the clutter of the vegetation or very flat surfaces. They used to.
That makes sense.
I mean, I know that the Argentinian colleagues for the SAOCOM, they use the deserts they have in Argentina or the flat areas they have in Argentina because you don't have the pollution of the vegetation.
Carlos, I was wondering, you showed many examples of bands of showing the correlation of sites. And I was going to ask you, which are the main drivers of decorrelation in images? You show that urban areas are very stable targets, but for the other natural targets, you understand my question?
Yeah, sure. I fully. I mean, this is a kind of $1 million question. I mean, there are many. There are many parameters that control the correlation between the SAR images. Some of them are quite technical. I mean, the how to say this. The miscorregistration, noise, etc. But not analyzing those decorrelation parameters that depend on the system and somehow they can be corrected up to a certain point. There are other points, or there are other correlation the correlation parameters that affect. First of all, is the volume decorrelation. I mean, whenever you have a volume, depending on the height, you will have more or less decorrelation. For instance, this is the basis for polarimetric SAR interferometry to obtain the height of the vegetation. Also, you have the moisture of the area. The higher the moisture, it seems that the lower the coherence. The movement of the leaves, this will decorrelate. I mean, there are many properties of the target that may decorrelate the signal. So therefore, some people say that these kind of behaviors are somehow random, someone would say chaotic. So they are very difficult to model, and therefore they are very difficult to correct if you want to correct them. You cannot. I mean, you cannot correct them, but you can obtain information. For instance, from the volumetric decorrelation, you can obtain the height of the vegetation. For instance, the next future biomass mission from ESA, which is a P-band SAR, will use this information to try to recover the height. The problem is that it will be contaminated by the temporal decorrelation between the acquisitions are acquired not at the same time. Okay?
Thank you. Rafael, I was thinking maybe if you want to make another comment, and then we can pass. We have several questions from the audience.
Yes, we have. If you want to start with this, we have people from the whole country, people from the whole world. We have people from Middle East, people from South America. A lot of different questions here. But as you started to talk about P-band, I work with P-band. and our system has full polarization, full polarimetric p-band. And I work with target detection and target classification under the forest with p-band.
Mm-hmm.
And I would like to ask you if you indicate any technique or any algorithm, if you saw something about this to improve or to improve our target detection under the forest. If you, I would like so much if you can help me.
Yeah, I would. First, I'm not an expert on. I mean, I know because I have read papers and colleagues. We have discussed about that. But maybe the first techniques if you have polarimetric data, that I will try to use is how do you call it? I forgot the name. Sorry, it's
No.
target decomposition theorems for polarimetry.
Okay.
Okay, because I mean, let's imagine that you want to detect a car below the vegetation. Okay, a car, I guess it will be dominated by double bounds and contaminated by the volume of the vegetation. So basically, what you can use is these target decompositions. You remove the part of vegetation and maybe you will have a better detection. Another of the techniques that you could use is what they are called polarimetric optimization. I mean, you use, or you try to look for the best polarization state that is able to discriminate your target. I mean, there is the work of Wolfgang Werner in the 70s doing polarimetric optimization, which is a quite classical approach. And therefore, as you have fully polarimetric data, you can make polarimetric optimization. And therefore, all the work of Jacob Van Zyl with polarimetric optimization, you can do that. I will start with both. I mean, target decomposition theorems and polarimetric optimization. These are the two techniques I would use. I mean, these are techniques not based on signal processing. They are techniques that fully exploit the polarimetric diversity. And then on top of that, you can use image processing techniques that can use to optimize your detection.
Okay, nice. I will do. Thank you very much.
Welcome.
Well, maybe we can start with a question from José Augusto Correa Martins. Carlos, he's asking you if you know if there is a good band combination to see burned areas.
Or the gradation.
Yes.
I mean, I have been working precisely on that problem, and I have done that with C-band and with L-band, and both were quite good to detect the differences. I mean, the issue is that the Barnett area is so different from the non-Barnett area that the detection of that Barnett area does not really depend a lot on the frequency. I mean, with any frequency, you can detect. Of course, if you have multiple images and multiple bands, you can combine, you can fuse them, and you can improve your information. In our case, when we were working on detection of Barnett areas, we found that also analyzing the temporal behavior was very useful, because the dynamics of the Barnett area were completely different from the dynamics of the non-Barnett area. Why? Because the Barnett areas are flat areas, so they are quite constant, and the non-Barnett areas, they are sensitive to the growth of the vegetation, so the dynamics of the vegetation. So maybe combining frequency with multitemporal acquisition, you can improve the detection of your areas.
Right. We have another question here from Flavia de Souza Mendes. First, she says that she's really enjoying this event. She's thanking, and she's also asking what are the challenges in implementing polarimetry in the process, not the results, in the Google Earth engine. If you know a bit about that.
Yeah, I have the problem, I would call it problem, or the limitation, let's call it limitation of the Google Earth engine, is that they use what they are called ground range products. So they use only the intensity in HH and in BB and BH. You don't have the product of correlation between the two. You don't have the coherence between the two. This is a limitation of the Google Earth engine.
Oh yeah.
So for instance, tomorrow I share another tutorial in Vietnam with a colleague that basically they are analyzing how to make available these interferometric products into a cloud service, for instance. For me, this would be the main limitation.
Yeah, I imagine that they don't have much options with Sentinel-1 data. It's a bit like, we call engessado, Yeah. Well, we have the next question is from Arsalan Ahmed Othman. He's asking if it was right, if it was 80% of the data for training and 20% for testing. Is that? Yeah.
No, we were using the opposite. We were using the 20% for 20% for training, 80% for tests, because we don't wanted to have overfitting.
Okay, thank you.
We even in some applications we use 1% training because we have many pixels. The advantage is that we have many pixels.
Okay. José Augusto asks again if there is an optimal deep learning approach.
Wow.
Data. Maybe everybody wants to know that.
Yeah, no, me too. Me too. Yeah, I would like to know. I mean, being serious. I mean, more than to focus on a particular deep learning technique, in the case of remote sensing, I would focus on the information I have more than into the technique. Of course, there are some techniques that can be better than others, but from the works we have seen in this project and the works we are currently doing with one of my students, is my opinion, and we can discuss, but this is a personal opinion. You can have higher improvements carefully looking at the input features than looking into the system, into the technique. Of course, some techniques will classify better than others, but the key point is the input features.
Yeah, it seems the way for that, because you have so many options. I was thinking about the target, the composition features that you can generate, like the alpha, angle, entropy, and isotropy.
For instance, just to give some elements, CNN, convolutional neural networks, they seem to have an advantage because they exploit the spatial correlation. They have these elements. Embedded into the network, so it seems that they work okay with that. But I have no experience. All what I know is from the papers I have read.
And Carlos, sorry if I don't know that, but have you published already the results that you presented us? Because it's such important.
No, we haven't. No, I mean, to be honest, I have no time.
No.
And we want to present those results in a book chapter. We are about to prepare. So I don't know, maybe, but I mean, I don't know if the report of my student is open. I can check and I can send the link to you if you want.
That would be interesting.
I don't know if it's public or not yet, because he finished just a few months ago, so it takes some time to make it public.
I think we have another question in here from Isabella. Regarding the urban classification, which strategy would be best to differentiate classes within the urban fabric?
I don't know. Honestly, I cannot give a real particular. I cannot give. I don't know. I mean, I cannot give. I mean, because I haven't worked directly in the problem. I mean, I have worked in problems, urban, non-urban, these very simple problems, but not into analyzing specifically that. So I don't know. Maybe you can use the different polarimetric signals. Maybe the polarimetric signature of some areas is different from others. But I would recommend Isabella to start to look at the polarimetric signature of the area she's interested into and try to discriminate and to see if she found some points that discriminate. Or to use deep learning if she has ground truth to train, and then to look into the network, how the network is classifying the areas. But I mean, I cannot really give particular answer to that point.
Yeah, I imagine that there's, in all cases, there's lots of things to be tested. So even for urban areas, that to me seem like the most easy area to differentiate because of the striking appearance that it has. Well, I don't know if somebody else has some other questions. Maybe, I don't know if Rafael wants to go back and say a few more words, because maybe it's time to say bye-bye. I don't know.
I have more questions if I have time.
Okay, then.
Carlos,
go ahead.
Please. You talked about the SH8 in the matrix, the SH8 plus SVV as a single bounce to measure half surface. Do you think that it's possible to do any soil classification with this, with polarization? Did you see? I read something about this.
Yeah, I mean, you have all the work from, I would say, early 90s from Eric Poitier, Yongsen Lee, basically, that were doing the first tries of classification using polarimetry, which are very, very important. These are very, very important works. And they establish the basics of classification with pulsar data. You have, instead of using directly the polarimetric features to classify, you can obtain some derived parameters like the entropy and isotropy alpha parameters to classify. You can also go to the work of Shine Cloud, where together with Eric Poitier, where they use this all these target decomposition theorems to to increase the number of features, so to have a better classification with that. I mean, with polarimetry, it's quite straightforward to distinguish between basic scattering mechanisms. You can distinguish urban areas from vegetation, from surface. I would recommend you to go on all the literature of target decomposition theory. Basically, it starts with Shane Cloud, Eric Patier, Jacob Banzal, Yoshio Yamaguchi from Japan. He did a lot of work on that. Also, some colleagues in India with Abhik Bhattacharya who are working on that. So, I mean, all the literature on target decomposition theorems that today is the most used to exploit polarimetric data. And there are plenty of techniques, very different techniques.
Nice. And other question.
If I may mention, I forgot. We have recently published a book on polarimetry, which is open access. So you have everything there, all the applications.
Oh, wow, that's great.
It's in, I don't know, Springer. Okay? It's a book. The editors are Yves Louis Desnos and Irena Heinzek, and the whole book is open access. So there is a small chapter on the theory, but most of the contributions are on applications. You have all the applications on polarimetry up to now there, and it's open access, so it's everything for free.
That's great.
Nice. Other question: if we compare with other sensors, like mainly with optical sensors, one of the advantages we have if we work with multitemporal SAR is that we can do a better registration between the images, between the acquisitions. And my question is, what is the main reason that allows a perfect registration between the multitemporal images in SAR systems?
Because the registration depends on the geometry, and you have a perfect knowledge of the geometry with Sentinel-1, and also depends on the image formation process. And these processes are, both of them, 100% controlled. So that's why you obtain such a good co-registration. I mean, for instance, with Sentinel-1, you have the ISA tool snap, where you have all the algorithms for co-registration already coded in there. And especially because interferometry with Sentinel-1 is only possible if you make a very good co-registration. But this is for free, open in SNAP, SNAP, which is the official tool of ISA to process data.
Okay. And I like it so much, talking about the artificial intelligence, I like it so much when you said that it must not be applied blindly. This is a very important thing to say.
I mean, I really like these techniques. I'm really attracted to that. I mean, also because I'm teaching here in Barcelona in a degree of big data, but as any tool needs to be adapted to the signal you are using. And this is the results we were showing here. If you apply blindly, of course, you obtain very good results. Of course, I mean, you obtain the best results. But the message I wanted to give is that you can do even more than beyond blindly applying. I mean, I did it blindly the first time, of course. I mean, everybody does. But if you go beyond those results, you can improve a lot your results. And you can optimize. And this is very important for me.
Yeah, I think so. We are experiencing now, to publish articles, you have to use, machine learning process. You can't just use a simple statistical analysis like a regression or correlation analysis. The editors want you to use machine learning. And of course, this is valuable and it's very important, but I don't think it's the only answer to everything, you know. And and I think the risk of doing what you are doing to apply blindly, maybe we can reach a point where we don't understand our results, you know, you just don't know why it was such a good accuracy or something. So I think this is very important, really, what you said. You have to understand what you are doing, what type of features you are putting inside a system, and
and also, I mean, there is an option now at the European Space Agency. They try to embed artificial intelligence into the satellites, on board the satellites. So normally these technologies are energy intensive. They use a lot of power. So you have not the luxury to have something that expends a lot of energy into a satellite. So therefore you need to optimize. That's why you need to obtain the best with the minimum energy possible. This is when you go into a satellite, because you have no nuclear plant in your satellite, so you cannot use infinite. So you have limited resources, and that's why that's why I like it, the results. And this is why I wanted to present these results.
Yeah, very interesting, very important, very relevant. Well, Rafael, you have any more questions?
No, thank you very much for today. It's enough. Thank you very much.
It was a pleasure for me to present this talk.
Carlos, it was wonderful. I hope we can have you again here, because it was very, very nice. And well, thank you a lot for being here with us. We were going to try to find this book with open access to.
Yeah, it's a Springer.
Okay. And well, thank you very much. Good luck for your work now. And
thank you for the invitation. I really appreciate it. I really like the invitation.
Okay. For everybody who is watching and listening to us, thank you very much. And I don't know if José is in. Would you like to say something, José?
I'm here to first of all, thank you, Professor Carlos Lopes. It was a really good presentation. I think that SAR is a very important tool to we understand how our world is changing and behaving. And I think that your presentation added much information to the public in general. You guys can keep talking. I'm here to do the encerramento, the ending of the presentation. If you have anything more to talk, you can talk, and I will end the presentation with one more announcement.
Okay, José.
Okay, so we will start to end the presentation, and thank you all for joining us today. Thank you, Carlos Lopes, for being this very good professional that can teach so much for everyone. Thank you, Tatiana. Thank you, Rafael Rosa. And we will have 16th of December, another presentation related to Qualis. Qualis is an index that we use in Brazil to guide the publications. When we write any article, we will try to consult Qualis to see that if that magazine is a good one. And I like to invite you all. Thank you.
Okay.
Yeah, we will be there. Thank you very much. Have a good rest of week.
All the best.
Ciao.
Bye-bye.
Bye-bye.
Bye-bye.